Okay, so I've got to keep to 15 minutes, including questions, so I'm going to get move on. I'm going to talk about global dispatch today. First of all, we're going to say what is a dispatcher. If you're not aware, dispatcher is what makes the decision about which lift should serve which call. In this example, I'm showing landing calls and car calls, but they could equally be destination calls. So if you think about a destination call as a combination of a landing call and a car call. So just to give you an idea of the problems that a dispatcher designer has to consider, if we've got 20 calls and 8 lifts, we've got 1.1 trillion options of the allocations of calls to lifts. It's exponential, it just goes up and up and up. So there are lots of different ways to make the choice, and if you're a student of Dr. Barney's work, you would know about the ETA algorithm, and at the most basic level, all you need to do is to say how long until you reach that lift, and you're actually minimizing what's called system response time, where you're trying to minimize clearing those calls as quickly as possible. Now, we could talk about artificial neural networks, we could talk about genetic algorithms, and we could talk about fuzzy logic, but we're not going to do that today. There's references in the paper, if you want it, the written paper, if you want to look at that. What I want to talk today is about the global dispatcher. And first of all, what do I mean by a global dispatcher? So I'm looking for a dispatcher, or developing dispatchers, which will deal with single deck lifts, will deal with double deck lifts, and will deal with 2 lifts per shaft, commonly known as twin. So my dispatcher is designed to deal with all of those at the same time, just that single dispatcher, deal with all those combinations. Obviously, you probably wouldn't put a twin lift with a double deck lift, but if you're going to be on a mix, you might as well mix everything together and have the same basis for your dispatching. We need to do it to be able to deal with conventional systems, so hall calls and car calls, and we want to deal with destination control as well, being able to enter your destinations at the landing and go to any destination. And also we want to deal with hybrid control, which is where you have destination input on some floors and conventional input on all floors. And I'm going to add another criteria for the global dispatcher. We need to be able to work with all controllers, which is actually more challenging than you think, and I'll explain why. And that's from painful experience. Actually, you can design a dispatcher to work with one controller, and you switch to another controller, and it doesn't work quite the same way. So, why am I so obsessed with this? And I have been working for many years. Because I write simulation software, I'm having to manage the development and maintenance of 14 current dispatching algorithms. So I've got all these different dispatching algorithms to do all these different combinations of things. Some of them overlap, some of them don't overlap. So I'm looking for one algorithm to do the whole thing. I only want to write one algorithm. It's going to be it's a big one, but I'd rather write one than maintain all those different algorithms. And I've been working on dispatching for about 36 years now, so sort of learned a few things along the road and trying to bring that all together into one main algorithm. And it's a bit like a mountain. It can be done. So that's why I'm trying to climb it. Some of the challenges that we've got with a global dispatcher, well, I mentioned about collective control. And collective control is the basis of most group algorithms. There are a couple of exceptions, but most algorithms will work like this. They'll serve all the calls in the up direction. And they'll serve all the calls in the down direction. Nice and simple. And in theory, all controllers, modern controllers, work that way. And if we knew they all worked exactly the same, I wouldn't need to worry about working with one controller or the other. But there are differences. So just to give you one scenario, so this is a lift going up to a call. It's going 2 down. Yeah, so we're going up and we're going to reverse and come back down to the second floor. So we might be on the 6th floor, we want to go down to the 2nd floor. Everything is okay with the world until we get another call. So another call now, this person wants to go 7 up. So they're both on the same landing, and then different controllers are going to deal with that in different ways. And one controller might actually say, actually I'm committed to going 2 down, so I'm going to reverse there. And another controller might say, oh, I can switch, because overall it's more efficient if I carry on up and pick up 7 up and then come back round and pick up the down call. So this is one of subtleties which, when you start building dispatchers which are transferred across different controllers, you have to deal with those sorts of issues, and they've got me unstuck in a few scenarios. So that's the problem, and what the solution is, or my solution to that, is to embed the collective control logic within the dispatcher. So that decision just becomes the decision of the dispatcher and not the decision of the controller. So I'm basically removing the intelligence, well, no, there's lots of other intelligence, dispatching intelligence, group collector controller from the controller and giving it to the dispatcher. And that basically means it's the dispatcher, is what it is saying, is going to go to this floor. It might change the target, so it might be travelling up to 10, but there might be a new call that comes in at 7 on the way up, so we actually have to decide whether or not we can stop. So changing the target of floor, and then also opening and closing the doors. So opening and closing doors, you would think is normally a controller function, but actually, as the dispatcher designer, I know things like how many people are expected to load and unload the car. So if I think there's one person going into the car and, getting out of the car, what I can do is I can say, the beams are being broken, the beams are being re-established, I can close the doors immediately. There's no longer a need for a dwell time. So I can save 2 seconds. Now in the world of dispatching, that's a lot of time. So if I can save that a few times every now and then, I'm going to save a lot of time. Obviously all the safety factors are still dealt with by the controller. So I'm only suggesting, I'm sending messages to say, please do this. There's nothing to stop the controller actually doing what it's told, but I'm suggesting what's the best thing to do. So some other issues that we have to deal with, like mixing conventional and destination calls. So this is done by converting conventional calls to destination calls. And what I'm doing here is I've got a 7 down call, and what I'm doing is I'm assuming it's a destination call, in this instance from 7 to ground. So all I've got is down 7, but I'm going to assume it's 7 to ground, and then later when the call is actually answered and the car call is inserted, we know it's going to 3. So I can update my estimate of destination from 7 to ground to 7 to 3. Single to multiple calls, so this is, I've got 3 people, the system doesn't know how many people are behind that call. It can make some estimates based on learning and so on. So what I'm doing now is I'm saying, okay, I've got 1 call at the moment, but when those 3 people get in, they've got different destinations. In this instance, they've selected 2 car calls, so I can translate my single destination call into 2 calls. If I had good load weighing as well, I could tell it was 3, and then I could then combine and improve even the way up to 3. The other thing, the advantage of treating everything effectively as a destination call, which is what I'm doing, is that we can do passenger-centric optimization rather than whole call response time. So traditionally systems have looked to clear the calls as quickly as possible. What we're trying to do and what we can achieve with destination control and then infer it with conventional control and the hybrid is actually we can minimize the, we can look at it from the passenger's point of view and seek to minimize waiting and transit times rather than system response times. Some of the other issues, so in double deck lifts, just as an example, we can have, we have to ban allocations. This example is if you want to consider the lower cab allocation, so if you want to consider this person going from 6 to 8, if you want to consider the lower cab as a possibility for having that person, but we've already got the upper cab stopping at 6, if we allocate to the lower cab, what's going to happen is the upper cab's going to arrive first and they're going to get into the wrong cab. And that's one of the issues you have with destinations. You have to deal with double deck lifts, you have to deal with that. And then on the 2 cars per shaft or twin, you get the impasse scenario where you've got one cab, actually the lifts want to switch over. So there's all sorts of problems that you have to deal with these if you've got more than one cabin in the shaft, there are all sorts of things that you have to ban. And Again, if you go in the reference of the papers, you'll see this sort of, this is the anti-collision algorithm to avoid the lifts crashing into each other. So this is basically how we're doing it. I introduced the global dispatcher interface here in 2016, so we've been working on this for a while. It's Ethernet network, and we're using TCP/IP, applying Google protobufers to transfer the data. So we're using modern networking technology, and our intention is to make that license free because we want other people to use our protocol. You can also, so this is in the real world, obviously. This is when you're using the global dispatcher, which is a separate device with a simulator, where you link it together again over the dispatcher using the dispatcher interface. And of course, you can run the dispatcher on the PC as well. So that's basically how it works within a simulation tool. So you've just got the dispatcher running as another process on the PC. So this is an IT device we're using. So it's future ready to post data to preventive maintenance AIs. We talked a lot about AI preventative maintenance. That's our intention, that the data is available, because one of the challenges that I've had over the years, is getting data out of lift controllers. There's a lot of data that actually comes to the dispatcher, which can be shared with AIs. Our next major simulation upgrade will allow for replay of the dispatcher within the simulation. So we're basically providing the same traffic analysis that you're using for design, post-installation for analysis. So basically the idea is that you design using simulator, you install the thing, and then you run the same analysis tool on the results. So early versions some of you might have seen early versions of this in Elevate 9. Some features are still under development. It's intended to be in Elevate 10, which is an online version of our software next year, 2025. No, it's the year after, isn't it? Year after, 2025. Big job making this online. We've actually been partnered with Leicester Controls since 2015 to demonstrate proof of concept. So we've been developing it in real systems, first implementations. We had it in our office in 2021. It's launched at LiftX 2022, and we're now rolling it out. Did I keep to time?
Pretty much.
Good.
Thank you very much, Richard.